Now next method is ring modulator. So in case of ring modulator, we will again have the message signal and carrier signal, but in ring modulator the diode is connected in the form of bridge, and through the transformer we give input to this bridge circuit. So let us draw the circuit diagram for this ring modulator. We are having a primary transfer or primary windings. So this is the primary windings, or here we are giving the message, and this is the bridge circuit. There are 4 diodes, D1, D2, D3 and D4. Now the output of this bridge circuit is input to the band pass filter. Having center frequency 2 FM, having center frequency FC and bandwidth 2 FM. And output of this band pass filter should be our desired result, that is double sideband suppressed carrier. We have to consider the circuit in such a way, or the band pass filter should be in such a way that the center frequency is FC, that is the carrier frequency, and bandwidth is 2 FM, then we will get the double sideband suppressed carrier, as we have seen in the balanced modulator, that this type of band pass filter can generate the same double sideband suppressed carrier that we have discussed in the types of amplitude modulation. But there is one thing which is missing here, that is carrier signal. So the carrier signal should be given into the input this particular circuit. So the carrier signal is given here with the help of center taping. So here we have applied this center taping carrier signal via this center taping, and this carrier signal is AC cos of omega CT. This is our carrier signal. Now as you can see that in this diagram, the message signal and carrier signal is applied. The carrier signal is applied via center taping of the transformer, and there are 4 diodes, D1, D2 and D3, D4, and it is connected in the form of bridge. So how does this circuit work? So now as you can see that because we always consider that the diode works on the basis of or according to the carrier signal, because the carrier signal always dominates compared to the message signal. So if we consider the amplitude of the carrier signal is much greater than the message signal amplitude, then this complete circuit will work according to the carrier signal. So, because the carrier signal is a sinusoidal signal, during the positive half cycle the diode will be forward biased, and during the negative half cycle diode will be reverse biased, as in case of switching modulator. But here there are 4 diodes. So, what will happen when the carrier signal is in the positive half cycle? So, which diode will be forward biased and which diode will be reverse biased, that we have to see, because the input signal, carrier signal, is also applied with the help of center tapping. So, because of that also the polarity will be different in across the different diodes. So, the different diode will be forward biased and other diode may be reverse biased. That we will see here. During the positive half cycle of this carrier, when it is in the positive half cycle, then the polarity will be distributed in this way. This is the positive half cycle, plus and minus. So, here we get the plus and here we get the minus, positive and negative, because here we are applying the positive half cycle. So, here also we will get the plus and minus, but in the lower half of the center tapping we get the polarity which is reverse of the upper half, because of the center tapping the lower half will be 180 degree shifted. 180 degree shifted means the polarity will be just inverted. It means that it is now minus and it is plus. Plus minus, so this should be plus minus and this should be plus minus, but because of center tapping this is just reversed and this plus is coming here and minus is coming here. Now, because of this plus sign, the diode D1, the positive polarity will come into the P side of this diode D1, and this diode D1 will be forward biased, and positive polarity is in the N side of diode D3, so it will reverse biased. And similarly, when the plus sign will go applied in diode D2, so it will be forward biased and the positive side is applied in the N side, so diode D4 is reverse biased. So, this is the case of positive half cycle of carrier. So, during the positive half cycle of carrier, diode D1 and diode D2 is on, and diode D3 and D4 is off. Off means open circuited and on means short circuited. So, what will happen when the diode will be short circuited and open circuited? So, let us draw the diagram separately. We have message signal at the input, this is short circuited, suppose at the input of this band pass filter VIT is the input and here output is V0T. So, the value of VIT, because the message signal is applied here and this is open circuited, and here also we get open circuited. Now, when empty is applied, suppose this is plus and this is minus, so here also the plus minus will get, here also we will get the plus minus, and this plus sign, because of this short circuit, this plus sign will be here, and because of this short circuit the minus sign will be here, mean whatever will be the message signal, that will come directly at this particular output transformer, and from here we will get the empty here, that means the VIT is equal to empty. So, VIT will be equal to empty during the positive half cycle of carrier. Now, during negative half cycle, what will happen, how we can assign the polarity. So during the negative half cycle, this is minus, this is plus, so this will be minus and this is plus and this is plus and this will be minus, because here minus and plus, so the 180 degree phase shift, so this is minus and this is plus, this is just inverted, so this is minus and this is plus. So because we have applied the negative polarity in the P side of this diode D1, so it is reverse bias, but the N side of this diode D3 is connected with the negative polarity, so it will be forward bias. So this diode D3 and this diode D4 is now working and it acts as a forward bias, and that is short circuited, and this diode D2 will be off and diode D1 will also be off. So now in this particular case, D1 and D2 off, that is open circuited, and D3 and D4 is on, that is short circuited. And according to this, if we draw the circuit diagram separately, this is open circuited, here we have message signal empty, suppose this is plus and minus, and it is short circuited. This diode D3 is short circuited and diode D4 is short circuited. So when we apply the message signal empty, suppose this is plus and this is minus, so because of this transformer, the plus and minus will be induced here, but this positive sign will have the path like this. So this plus sign will go into this side, that is this is plus. Now this minus sign is having the path, this is short circuited, so it will get this path, and this minus sign will be assigned here, because there is no path, that is open circuited, so there is no path, so this positive polarity will not directly appear in the output transformer, it will actually invert. Because of this cross connection, the positive sign will get here and the negative side will appear here. So according to the input, this is plus minus, but here we are getting minus plus, that means the output, at the output the message signal is inverted. So here we get VIT as minus empty. So when during the positive half cycle VIT is empty, so as it is the message signal will appear, but in the case of negative half cycle of carrier, the message signal is inverted. So we have two conditions. First is VIT is equal to empty for positive half cycle, and minus empty for negative half cycle of carrier. Both we are talking about carrier only. So now we have to generate the double sideband suppressed carrier. So how can we generate this double sideband suppressed carrier? And we have to prove it mathematically, as in case of balanced modulator we proved that at the output of that balanced modulator we are getting the multiplication of message signal and carrier signal. Once we get the message signal and carrier signal in multiplication, we can say that it is generating a double sideband suppressed carrier. So if we combine these two equations, whenever the diode comes into the picture, the mathematical analysis can be done when we take the condition of diode switching. So when the diode works as a switch, so there is some on and off condition, and here also we are having on and off condition, and whenever we have on and off condition, we can periodically change this on and off condition with the help of periodic square wave. So we can combine these two equations, like VIT is equal to PT, there is some signal PT, and multiplied with empty. So what should be the behavior of this PT? This PT should be plus 1 to get this result. This PT should be plus 1, but provided this should be for positive half cycle. So the time period of carrier is Tc, because the carrier is having frequency Fc, so it is the time period having Tc. So for the half time period it should be +1 to justify this particular condition, and for other half time period it should be -1 to satisfy this condition, negative half cycle. So in case of negative half cycle it should be -1, so this Pt will be -1, so we will get -mt, that means our this condition will be satisfied. And when for the positive half cycle this Pt is +1, then we will get the +mt, so our first condition will be satisfied. So what should be the value of this Pt? So this Pt should be a square wave this should be the value of Pt, and this Pt is +1 and -1. For half time period, that is Tc by 4 minus and plus Tc by 4. So this duration is half time period, and this is 3 Tc by 4, and this should be Tc, the time period of this signal, and this is minus Tc. So now this is a periodic signal. This is a periodic signal with time period Tc. So during the positive half cycle, that means half time period, this is the half time period, this is half time period, the width is Tc by 2, this is +1, so our first condition will satisfy, and during this half time period this is -1, so our this condition will be satisfied. So to get the mathematical equation, we have to multiply Pt by Mt, and this Pt is a periodic signal, so it can be represented by trigonometric Fourier series, and we have to calculate the trigonometric Fourier series of this Pt, and then we will multiply it by Mt, and we will see what are the frequency component comes. And because the output Vit, this Vit is actually input to the band pass filter, then the band pass filter is having characteristics Fc and bandwidth 2fm, so we can find the output of this band pass filter once we know that the input to the band pass filter, which is Vit. So we will calculate the trigonometric Fourier series, and this trigonometric Fourier series is given by, the periodic signal is Pt, it is given by A0 by 2 plus summation n equal to 1 to infinity an cos n omega ct plus bn sin n omega ct. So one by one we will calculate the value. So let us calculate the value of A0. This is 2 upon time period is Tc, integration from minus Tc by 2 to Tc by 2 Pt dt. We have to integrate over the time period. So minus Tc by 2 to Tc by 2, if we integrate minus Tc by 2 to Tc by 2, we will get one time period. So for this we have to integrate from minus Tc by 2 to minus Tc by 4, then minus Tc by 4 to Tc by 4, and then Tc by 4 to Tc by 2. That means we have to divide the whole integration in 3 parts, 3 sections. So we can also write this as 2 upon time period integration from minus Tc by 4 to 3 Tc by 4. This is also one time period, because if you take the difference between these two, 3 Tc by 4 minus of minus Tc by 4, you will get the complete time period Tc. So this can also be the integration limit, because we have to integrate over the one time period. So the limit should be in such a way that one time period should be covered. So if I take the difference between these two, Tc by 2 minus of minus Tc by 2, we are getting one time period. Similarly, if I take the difference between these two, we will get one time period. So for this the integration will be easier, because we have only two sections. One is minus Tc by 4 to Tc by 4, and the value between minus Tc by 4 to Tc by 4, the value of Pt is constant, that is 1. So, this is 1 into dt, and plus another half, that is Tc by 4. Here Tc by 4 to 3 Tc by 4, the value is minus 1. So, here we will get minus 1 into dt, Tc by 4 to 3 Tc by 4. If you solve this, you will get 2 by Tc. Here we get Tc by 2 with plus sign, and here we get minus Tc by 2, that means 0. So, value of A naught is 0. Now, we have to calculate the value of An. If you integrate, you will find this Tc by 2, because this is half time period. So, integration is nothing but the area. Area, that means minus 1 into this time period. So, we get minus Tc by 2, and for this we have to calculate this area. So, for this upper half we get calculate area, then this base is Tc by 2 and this height is 1. So, we get Tc by 2. So, this is Tc by 2 and it will get cancelled, and the answer of value of A naught is 0. Now, we will calculate the value of An. So, what is the formula for An? Formula for An is, again we have to consider one time period, and the time period we will consider from minus Tc by 4 to 3 Tc by 4, as we have seen that it is easy to integrate if we consider this time period, because we have to break into only two section, that is minus Tc by 4 to Tc by 4 and Tc by 4 to 3 Tc by 4. So, we will consider the same range to calculate value of An, and the value of An is 2 upon time period, integration from minus Tc by 4 to Tc by 4, value of Pt is 1 and this is An. So, we have cos n omega Ct dt minus Tc by 4 to 3 Tc by 4. Here we have minus sign because the amplitude is minus, and cos n omega Ct dt, bracket close. Now, we will integrate this 2 by Tc. Cos, integration of cos is sin n omega Ct divided by here n omega C, limit from minus Tc by 4 to Tc by 4 minus again sin n omega Ct divided by n omega C, limit from Tc by 4 to 3 Tc by 4. Now, n omega C is common in both. So, we get n into omega C into Tc. So, omega C into Tc can be written as, omega C can be written as 2 pi Fc, and Fc can be written as 1 upon Tc. So, omega C into Tc is nothing but 2 pi. So, here we have 2 pi, and in bracket we will get sin upper limit. So, sin n omega C Tc by 4 minus of sin lower limit, which is negative. So, minus n omega C Tc by 4 minus upper limit. So, sin 3 n omega C Tc by 4 and again lower limit. So, minus, or here is also minus. So, it will become plus sin n omega C Tc by 4. Okay, because this is the lower limit, that is why minus sign should be coming, but because of minus sign already present here, that will become plus. So, this is plus, and this minus minus is also plus, and this is plus n omega C Tc by 4, n omega C Tc by 4, n omega C Tc by 4. So, there are 3 times of n omega C Tc by 4. So, we will get 1 upon n pi 3 sin n omega C Tc, and omega C Tc is 2 pi. So, we will get n pi by 2. You can see here, this is omega C Tc is 2 pi, and 2 pi by 4, that is pi by 2, and n is already there, so n pi by 2, and this is coming 3 times, 1, 2 and 3. This minus and minus become plus, so that is why there are 3 terms. So that is 3 sin n pi by 2 minus sin 3 n pi by 2. Here also omega c Tc is 2 pi, so 3 n into 2 pi by 4, so we get 3 n pi by 2. So this is the value of an, this is the value of an, and value of Bn is 0. Why the value of Bn is 0? Because this is even signal, it is symmetrical about y axis, so this Pt is symmetrical about this y axis, and that is why the value of Bn is 0. So we do not need to calculate the value of Bn. Now we can directly substitute the value of A0, An and Bn in our original equation, that is Pt, and then we can multiply it by Mt to get the Vit, which is input to the band pass filter. So value of Pt, A0 by 2, A0 is 0, plus summation n equal to 1 to infinity An, An is 1 upon n pi 3 sin n pi by 2 minus sin n pi by 2 multiplied with cos n omega ct. So multiplied with cos n omega ct. Now this Pt should be multiplied with Mt to get the Vit, but before that we will expand this Pt and then we will multiply it by Mt. So if I substitute n equal to 1, I get 1 upon pi here and 3 sin pi by 2, and sin pi by 2 is 1, and sin 3 n pi by 2 here. So sin 3 n pi by 2, what is the value of this 3 pi by 2? That is minus 1. So if I substitute n equal to 1 here, n equal to 1, then we get sin equal to sin 3 pi by 2, and sin 3 pi by 2 is minus 1. So this minus minus become plus, so plus 1, and here plus 3, so plus 3 plus plus 1, 4. So we are getting 4 upon pi sin, this is already 1, and here n equal to 1, that is cos omega ct. Now when we substitute n equal to 2, so n equal to 2, that means sin, if I substitute n equal to 2, we get sin pi, and sin pi is 0. When we substitute n equal to 2, 2 and 2 get cancel and we get sin 3 pi. So this is also equal to 0. So this term will be 0 for n even, n equal to 2. And when we substitute n equal to 3, n equal to 3 means we get 1 upon 3 pi here, and here 3 pi by 2, so 3 pi by 2 is minus 1, so here we will get the minus 1, that is minus 3, and sin 9 pi by 2, for n equal to 3 we get sin 9 pi by 2, which is equal to sin 4 pi plus pi by 2. Sin 4 pi plus pi by 2 is nothing but sin pi by 2, and sin pi by 2 is plus 1. So here also we get plus 1, which with minus sign was already present here, and here we were getting minus 1. So minus 3 minus 1 is minus 4. So we get minus sign here and minus 4. We are getting minus 4 with cos n equal to 3. So 3 omega ct. It means that we will get only odd harmonics. It is called odd harmonics because 1, 3, and next when we put n equal to 4, n equal to 4 we get sin 2 pi, here also we get sin 6 pi, so it is 0, integer multiple of pi of sin is always equal to 0, so we will get this result with alternate plus minus. Now we multiply it by Mt to get Vit, so this Vit is multiplied with Mt 4 by pi cos omega ct divided by 4 by 3 pi cos 3 omega ct plus 4 by 5 pi cos 5 omega ct and so on, and minus sign and so on. You will get the result like this. Now this is input to the band pass filter. You can see that this is VIT and this VIT is input to the band pass filter, or here we are getting only the multiplication of message and carrier. Here the message signal which was input to the ring modulator and the carrier signal which was input to the ring modulator, both are not present. It means it is balanced about both, because at the input of band pass filter both are not present. That's why we will call it as balanced about both. Both MT and AC cos omega ct are not present at the input of band pass filter. Hence it is called double balanced modulator. Ring modulator is called double balanced modulator because it is balanced about both carrier and message signal, because both are not coming, that means it is balanced about both. Now when we multiply the message signal with carrier signal FC, we will get FC plus minus FM. When we multiply the message signal with carrier signal having frequency 3FC, we will get 3FC plus minus FM and so on. So at the output of band pass filter, what will come? At the output of band pass filter, V0 T is 4 by pi MT into cos omega CT. This will be the output, because if we draw the spectrum of this VIT, we can easily observe that the first term will be centered to FC. It is centered to FC and it is FC plus FM and FC minus FM. The next component will be centered to 3FC. This will be centered to 3FC and this is 3FC plus FM and 3FC minus FM. And the other component will be centered to 5FC, and there will be infinite terms. But this is the component which is centered about FC and having the bandwidth 2FM. This is having the bandwidth 2FM and centered about FC. So it will pass through the band pass filter, because the band pass filter which is placed in the diagram is having the center frequency FC and bandwidth 2FM. So our desired result is centered at FC and bandwidth 2FM. So this is the double sideband suppressed carrier signal, and this will be rejected by the band pass filter, and we will get the output 4 by pi MT cos omega CT. So this is the output of ring modulator, which is double sideband suppressed carrier. So in this way we can generate double sideband suppressed carrier signal with the help of ring modulator. So we have two methods. First is balanced modulator, which is single balanced modulator because it is balanced about only the carrier term. Message signal was present at the input of band pass filter, that's why we called it as single balanced modulator. But in case of ring modulator, at the input of band pass filter, both message signal and the carrier signal are not present. That's why it is called double balanced modulator, because it is balanced about both message and carrier. Now we can also draw the time domain waveform, because we have written here this VIT is multiplication of message signal and carrier signal. Periodic signal. So this VIT is PT into MT. So we can draw this also. If our message signal is sinusoidal, if this is the message signal, and suppose this is our periodic square wave, this is PT, and in time domain these two signals are multiplied. So when we multiply these two signals, we get the output when we multiply these two. We get the output when we multiply these two. This is positive plus 1 and it is also going positive. So this plus 1 with multiplied with this, because the constant term is multiplied with variable signal, so we will get the variable signal. So here we will get the variable signal, because suppose you multiply 1 with 0.1, you will get 0.1. The other input is constant, so we multiply with 0.15, we get 0.15. So whatever will be the value of variable signal, you will get the signal at the output. So here this is variable because it is 0 starting and then it is varying from 0.1, 0.15 and reaching to the peak value. So similarly we get the output in the same way. But once it goes into the negative side, so it will multiply it with the -1 suppose. So if you multiply -1 with 0.2, then you will get -0.2, that means you will get the negative value. So the value is now negative. So in this way we will get the output. Depending on the value of input and this square wave, we will get output like this. So this will not be present here, you will get this signal at the input of band pass filter. You can draw like this. So you will find in some standard textbooks the waveform like this. So this is the output of ring modulator, which is input to the band pass filter. Means it is having some periodic signal, it is having number of harmonics. So this number of harmonics are this VIT. So these are all input to the band pass filter, and then this band pass filter will give you desired result, because we have placed the band pass filter as per our requirement. So that's why this will generate a double sideband suppressed carrier. So this is all about the generation of double sideband suppressed carrier.